Hello, and welcome to my channel. Today, we're exploring the essentials of reading electrical drawings from scratch. Whether you're just starting or need a refresher, I'll guide you through each element step by step, from understanding the title block to identifying components and wiring paths. Electrical drawings are the roadmap to any electrical system, and mastering them is key to safe, efficient troubleshooting and maintenance. So, stick with me as we break down every section, making it easy and clear. Let's get started. First is the title block is usually located in the bottom or bottom right corner of the drawing. It contains essential information that helps identify the drawing's purpose. In this case, it shows a description labeled decanter bowl, indicating the drawing pertains to this part of the system. The original equipment manufacturer, or OEM, is listed as GEA Westphalia Separator, identifying the equipment's manufacturer. You'll also see a field labeled Drawing Number, which is 26 out of 74. This unique identifier is used to track and reference the specific drawing in a larger document set. The title block may also include revision history, which records updates made to the drawing, and approval signatures, indicating the drawing has been reviewed and authorized for use. Understanding these details is crucial as they provide context about the equipment, manufacturer, and version of the drawing, helping locate this specific page within the complete project documentation. Moving across the page, you will notice that the drawing is divided into sections. These sections are usually labeled with numbers or letters, typically ranging from 0 to 9 along the left or top side of the page. Each section contains specific components or parts of the circuit. For example, Section 0 might include the main power supply components, while Sections 1 through 9 could feature control elements, motor wiring, relays, or contactors. This numbering system is designed to help you quickly locate specific parts of the circuit. It simplifies troubleshooting and enhances your understanding of the overall flow of the system. Before we explore the further details of the drawing, I would like to explain the concepts of electrical circuits and control circuits to my students all over the world. This fundamental knowledge will enhance your understanding and clarify how these systems operate together. Let's begin with the electrical power circuit for the motor. This circuit consists of several key components that ensure the motor operates safely and efficiently. The MCCB, also called molded case circuit breaker, is a crucial component in any electrical system, as it protects the circuit from overcurrent situations that could lead to serious issues. When the current exceeds safe levels, whether due to a fault in the system, equipment malfunction, or external factors, the MCCB automatically trips, effectively interrupting the flow of electricity. This action prevents potential damage to not only the circuit itself, but also to connected equipment and devices, ensuring the overall safety and reliability of the system. Additionally, MCCBs can be reset once the fault is cleared, allowing for quick restoration of service without the need for replacement, making them a cost-effective choice for circuit protection. Next is the magnetic contactor. Magnetic contactor is a vital component in motor control circuits, functioning as an electromechanical switch that connects and disconnects power to the motor. In its default state, the contactor prevents electricity from reaching the motor. When the local push button, or PLC, programmable logic controller, sends a signal, either from a start button or based on predefined conditions, the contactor engages, closing its electrical contacts and allowing current to flow to the motor, initiating its operation. Designed to handle high inrush currents, the contactor ensures a reliable connection and smooth operation. When the push button, or PLC, sends a stop signal, the contactor disengages, cutting off power to the motor and safely bringing it to a halt. Additionally, many contactors feature auxiliary contacts that provide feedback to the control circuit, indicating the motor's status and enhancing system reliability. This functionality is essential for precise control in automated processes while maintaining safety and efficiency. Overload relay, OL. The overload relay protects the motor from overheating by monitoring the current flowing through it. If the current exceeds a set limit for too long, The overload relay interrupts the circuit, preventing damage. Finally, we have the motor itself, which serves as the load that the entire circuit is designed to control. Understanding how each of the previous components, like the circuit breaker, contactor, and overload relay, work together is essential for effective motor management. When all these components are in place and ready, the motor is prepared to start as soon as it receives the command through the contactor. This coordinated operation ensures the motor runs safely and reliably when needed. I want to clear my students that there are sets. There are two main ways to control a motor. One is electrical control, which I already explained, and second is the PLC control. With electrical control, we use simple switches and wires directly connected to the motor. You turn the switch on, and the motor runs. It's easy to understand and works well for basic tasks. But if you want the motor to do more complex things, like start and stop at certain times, you'll need more electrical parts, which can make it tricky. A PLC is a very powerful tool in controlling machines, motors, and many other devices in a factory or industrial setup. Unlike a simple switch, a PLC allows us to tell the motor exactly when and how to run. You can program it to start the motor at a specific time of day, stop it after a set number of minutes, or even control multiple motors at the same time. It has the same setup to the motor through the programming as we did with the electrical control. It has advantage that you have to use less wiring and more productivity as per requirement. In case anything to change process-wise, you just need to change the program instead of wiring. This is the basic advantage of using PLC. Both the circuits aim to run the motor when K1 contactor energize, either through the electrical control or PLC control. When the K1 energize, it will pass the electricity to run the motor. Anyways, it was an overview for my students to don't get confused in motor start and stop through electrical circuit and programmable logic controller. Moving to the drawing, we can see that the main component here is the VFD, or variable frequency drive. Each component in the drawing is identified by its unique tag for easy reference and identification. Here, the VFD is represented by T1. Now identify where this component is located in the panel. We refer to the drawing. This is essential because the drawing provides a clear layout of each component's position, allowing us to locate the VFD and other components accurately within the panel. Here you can see the two VFDs. Now the question is, which specific VFD is shown in the drawing? This can be identified using its tag. Let me zoom it for you guys to see clearly. This particular VFD shown in the drawing is also visible here in the panel. However, a question arises. In the drawing it's tagged as T1, but in the panel it appears as 01 plus MCC-T1. Let me explain this tag to provide clarity from the drawing for better understanding. I've added the drawing and physical picture in the same frame to make it easier for you to follow along. In the drawing, it's labeled simply as T1, while in the picture, it's marked as 01 plus MCC-T1. This difference is because the drawing tags are based on title block information or page numbering. Here, the VFD labeled with T1 from the drawing, and the title block information showing 01 plus MCC. When we join them together, it will become 01 plus MCC-T1. I hope you understand this concept. Let's move to the other components in the drawing and go through them as examples, just as we did previously. Here we're taking the breaker as an example to read from the drawing and locate it in the panel. The breaker could be tagged as Q1, F1, or another designation, as different countries have different standards. In this drawing, it's labeled as F1. From the title block, it's showing 01 plus MCC. And if I join it together, it will become 01 plus MCC-F1. Let's have a look in the panel picture for the clarity. Either it's the same tag or different. Okay, Here you can see the same tag after combining the title block information with the component identification tag that is 01 plus MCC-F1. I hope with the help of drawing, you are able to identify the panel components easily. Let's move to the another example of PLC signals to identify them in the drawing and see how they connect and transfer to the PLC. It's very simple, just like we did before. Here we have two analog signals going to the PLC from the VFD. Let's see how the drawing guides us to locate motor current bowl signal to identify. You can see it giving us the direction that from VFD terminal number 42, it going to PLC analog input channel, PIW7521, typically refers to a specific channel or tag associated with an analog input card in a PLC, which will help to identify the channel. Next is 0/47.4, which means this signal going to page 47 and section 4. All right, and then it's terminal 3. Let's move to page 47 and section 4 to find out this motor current bowl signal there. Okay, I've opened page 47. And here we can see section 4, where the PLC card is located. This is where the motor current bowl signal is being fed into the PLC. I'll also show you the physical terminals to help you understand it better. I hope you now have a better understanding of how to read electrical and control drawings. If you found this helpful, please like and subscribe to support my efforts. And don't forget to press the bell icon to get notified of my latest videos.